Hello friends, hope you are well. Welcome you all in my YouTube channel. I am Dr. Muhammad Sirajul Faizi, Assistant Professor, Department of Chemistry, LS College, Muzaffar. Friends, today in this video, I am going to explain about cycloaddition reactions. What is the cycloaddition reaction? The cycloaddition reactions are intermolecular pericyclic process involving the formation of a ring from two independent conjugated systems through the formation of two new sigma bonds at the termini of the pi system. The reverse process is called cycloreversions or is referred to as retroreactions. So look at this. This is the LUMO and this is the HOMO. This is side 2 and this side 2. Suprafacial. So this orbital of alkene and this one is also alkene. This one is ethene and 1,3-butadiene. So these reactions happen here. You see this and this and this and this is the matching symmetry. So cycloaddition reactions. A cycloaddition reaction involves the formation of two sigma bonds between the termini of two independent pi systems, resulting in ring formation or reverse process. Cycloaddition reactions are stereospecific. I repeat, cycloaddition reactions are stereospecific. Example, cis-trans isomers. The stereospecificity being afforded by superficial or intrafacial nature of the approach of the two pi unit in the transition state. The superficial or intrafacial process involved in the sigma bond making process is controlled by HOMO-LUMO interactions. What? HOMO-LUMO interaction of the two pi system in the transition state. The questions of FMO molecular theory can answer. FMO, frontier molecular orbitals. Look at here. This is 1,3-butadiene, this is 1,3-butadiene. At 150 degrees Celsius, in 10 days, it will come like that, forming these products through this transition state. Yield is 85%. You see, two ethene undergo reactions forming this transition state and 0% yield. Now you see, at 185 degrees Celsius, 900 atm, 17 hours, this transition state forming 78%. So frontier molecular orbitals explain difference in rate of cycloadditions. This is the 90% if you have the CHO group like that. If you have this system, then 92%. If you have these systems and these two withdrawing groups, 4 hours, this product 80%. Look at this diene and dienophile, 25 degrees Celsius, you will get this product through this transition state. Through this transition state, if you have the trans, then these products. So if you have this diene and dienophile and diene at 20 degrees Celsius, 1 year, 64%. It is for this transition. Through this transition, you will get two products. 90%, 1%. So analyzing cycloaddition reactions, you have diene, you have dienophile, interactions of the termini of two pi system. This is transition state, interaction of the termini of two pi system and forming this product. So interactions is between the HOMO of one pi system with the LUMO of the second pi system such that the energy difference is least. So terminology. New bond to the same side of the pi system. Suprafacial. Intrafacial knee bond to the opposite side of the pi system. This is intrafacial. So difference between suprafacial and intrafacial. So 4n plus 2 pi electron system, cycloadditions, transition state. In general, conjugated diene, alkene, dienophile forming cyclohexene via this transition state. Mechanistic feature, concerted mechanism, 4 plus 2 cycloaddition, pericyclic, concerted reaction that proceeds through a cyclic transition state. Only the S-cis conformation of the diene can react. So about 90% of molecules are in the S-trans form, S-trans and S-cis. So S-cis is better, S-trans. So this is the higher free energy and this is this diagonal rotations. This amount kilojoule per mole, 50 kilojoule per mole. This is 12 kilojoule per mole. And this cis, S-cis and S-trans in equilibrium. So this is diene, dienophile, transition state, new bond. What makes reactive dienophile? The most reactive dienophile have an electron withdrawing groups directly attached to the double bond here. Typical electron withdrawing groups. So superficial interactions, 4n plus 2 pi electron transition state. You see superficial, HOMO, LUMO. This is in phase, superficial, pi xs, pi ys, number of pi electrons in each components, superficial. Diels-Alder cycloaddition reaction, 6 pi electrons, transition state. This you look at this superficial and transition state, 6 pi electron transition state. Remember it and forming this product. So this is the same. The Diels-Alder reactions is an extremely well studied cycloaddition reactions. The reason for this is that careful design of the diene components and in component. The dienophile has led to a great insight into reaction mechanism. So Diels-Alder reaction transition state, this is diene, dienophile, electron withdrawing groups. This is the transition state, psi to LUMO of dienophile and psi to HOMO of diene. 6 pi electron system, superficial making these products. So diene, dienophile, if it is a trans, forming, you see, superficial, these products. So phi 4s plus phi 2s, that is enantiomers. These are enantiomers. So one of two equally likely transition states, enantiomers formations. So if you have this electron withdrawing group in dienophile, in diene, top you have this, bottom you have this, you see same phase. If you have this, you have is the same phase with this bottom. So you will get this enantiomers pair through this transition state and through this transition you will get this. So examples how you make this product 100 degrees Celsius. So via these mechanisms, examples, if you have this diene and here dienophile 100% yield, via this transition state you see diene and you have dienophile 98% yield. Diels-Alder reaction is stereospecific. Scene additions, cis-trans relation of substituents of alkene is retained in the product. The most reactive dienophile have an electron withdrawing groups directly attached to the double bonds. State-specific scene additions. Cis-trans relations of the substituents of alkene is retained in the product. The most reactive dienophile have an electron withdrawing group directly attached to the double bond. The most reactive diene have an electron donating releasing group ERG directly attached to the double bond. Example OR ether. So diene, dienophile, only S-cis conformations of diene can participate in the Diels-Alder reactions, only product, but it is enantiomeric. You see, you have the diene, dienophile, you have these two product is the same. You have this diene, dienophile, only product, orbital and chemical reactions. A deeper understanding of chemical reactivity can be modeled using frontier orbital of reactants. Electron flow from the highest occupied molecular orbital, HOMO of one reactant, to the lowest unoccupied molecular orbital, LUMO of other. So this is your diene, dienophile transition state product. We can illustrate HOMO-LUMO interactions by way of Diels-Alder reaction between ethylene and 1,3-butadiene. We need only consider only pi electrons of ethylene and 1,3-butadiene. We can ignore the framework of sigma bond in each molecule. So reactant HOMO and LUMO, you look at here, psi 1, psi 2, psi 3, psi 4, psi 5, psi 6. This is the HOMO, this is the LUMO. So here overlapping orbital have the same color, are in the phase. You see diene, dienophile, diene, and involving these orbitals. This bridge has one carbon atom. This bridge have two carbon atom, larger bridge. So XO NT2 larger bridge, SYN2 larger bridge. This is, you have dienophile, diene forming Indo product. You see. So one carbon bridge, two carbon bridge, longer, Indo and XO products. Secondary orbital overlap favor the Indo product formations. You see secondary interactions. Secondary orbital overlap in the Indo transition state, Indo products. New bonds, this. No secondary orbital overlap in the XO transition state, XO product. So this is Indo, this is XO. So look at this primary interactions, bond formations, and secondary interaction bond formations. HOMO, diene, LUMO, dienophile. So HOMO, diene, dienophile is electron withdrawing group, favorable, and psi 1, psi 2, symmetric, anti-symmetric, symmetric, anti-symmetric, pi 1, pi 2, pi 3, pi 4. This is the HOMO, this is the LUMO. So HOMO alkene, HOMO minus LUMO gap. So normal electron demand in Diels-Alder calculations, electron withdrawing group should be forming these products, diene, dienophile, and electron donating groups. So 1,3-diene, yani diene should contains electron donating groups. So you see, you will get these products except this. So here extending conjugation G, electron withdrawing groups, electron donating groups. This is the product. Substituents and dissymmetric of orbitals. You look at here diene. So it is this way. Now you see this change the shape. Diene you have like this. You see now this, there is a change if you substitutions. So large coefficient interactions and a small interactions, large small large interactions. So this is comfortable. Low energy transition state, high energy transition state, despite more pronounced steric interaction. So friend, rule for cycloadditions: number of pi electrons, thermal and photochemical. 4n, SA and SS. 4n plus 2, SS and SA. Opposite. S for suprafacial, A for intrafacial. So utilizing FMO to predict the stereochemistry